Hi, welcome to this lecture on mathematical methods. We have been discussing how to use sine series and cosine series, which is called Fourier series, to represent a function. In this lecture, we will discuss a related topic which is called a Fourier transform. So, today's topic is Fourier transform. In this lecture, we will answer two questions. First, we will answer what is Fourier transform, and we will discuss how is it useful. Before that, let us just remind ourselves that we have this Fourier series where any function f of x, which is a periodic function, can be written as some combination of some series of Cn e power I n x. This e power I n x can be written as cos and sine. So, it could be written as a summation of cosine series and a sine series, but the idea is that any periodic function f of x can be written as sum over n Cn e power I n x. Now, the Cn values, if I know e power I n x is cos n x plus I sin n x. So, if I know Cn, I can calculate f of x for as a function of x. Now, how do we get Cn? We can get Cn by inverting this integral, that is multiplying this function with e power I n x or minus I n x appropriately, and by doing this integral we can get Cn. This is something that we learn. And what is happening here? What is happening essentially is that if we want to specify some function, let us say the function which looks like the sine, looks like the sine function, we can either specify all the points, we can specify the data like this, or we could specify the frequency, which is something which I will discuss now. So, let us think of two functions, sin x and sin 2x. So, what is plotted here is two functions. One is sin x and one is sin 2x. What is sin x? The red curve is sin x. What is shown here in red is sin x. So, between 0 and 3.14 radian, so which is pi radian, which is 3.14. So, this is and there is 0 at 3.14 and goes and then again comes back. So, this red curve is sin x. Now, the blue curve is sin 2x. So, by the time sine takes one full turn, sin x takes one full turn, sin x takes two full turns. So, instead of either I can specify the data points for this, or I can specify just the frequency 1 and 2. If I know that it is a sine function, I have to just specify the frequencies. If I specify the frequencies, I can get the function itself. I can reproduce. If I just tell you 2 as a code word, and you already know that the function is sine, like you know the sine 2x and you can plot it. So, either you can specify the function itself or you can specify the frequency, and these can be useful and equivalent at some point, and this is very useful. So, for example, imagine a function which represents the wave in space, which is f of x. You can imagine a different function which represents the wave given its frequency, like as a function of its frequency. So, you can represent g of k or g of omega. So, you can just think of a function. So, let us think of some wave, some function. This could be, like, let us say any function you like. It could be even a music, right? You have a music which could be like sound increasing and decreasing. Now, instead of specifying this, which is f of x, I could specify some g of k, which is how often it repeats and what is its frequency, wave nature, etc. So, as a function of k, maybe it is as a function of k, it could be like 0 everywhere, and some k it will have some value, and then it will have again come back to 0, or it could be like this. It could, I don't know. It could have various shapes. So this is two functions you can see. Both could represent the same thing. So, and this is something that we will tell how to do that. So the way we can transform a function in real space, which is in paper, in typical real space is a function of x, to an equivalent function of in the frequency domain is known as Fourier transform. So Fourier transform is going from the xyz space to a frequency space or a k space. So now frequency could be spatial frequency or a temporal frequency. So you could have something as a function of x, where you could get something as a function of k, where k is essentially 2 pi by some length. So which is x is in length. So this is the inverse dimension of length. So 2 pi by some length scale would be like your k. So typically it will be n 2 pi by L. So often this n pi by L or n 2 pi by L, depending on this way you could write, you can define k appropriately, but k will be proportional to 1 over length. So this is one way of defining frequency in the spatial frequency. So the k is inversely proportional to L. This equivalently you could also have temporal function, that is f as a function of t, from which you can get g as a function of omega, which is a temporal frequency, where omega is some time function, right? It could be 2 pi by some time, right? So it could also be some n pi by some tau, some time function. So omega and time has, omega has inverse dimension as time and k has inverse dimension as length. So this is length inverse, this is time inverse, and you could either specify this function or specify this function, that would be equivalent. Here you could either specify this function or specify this function, those are equivalent, but specifying this, for example, can be very useful at times. That is one reason to do this. Second, using calculation in this space, calculation of things as a function of k could be very useful. For example, if you want to solve a differential equation, if you convert that equation into the k space, if you do this kind of a conversion from f to k, g of k, it is going to be very useful with something that is useful. Some very often experimental data will be in this space, it could be in this space. So therefore, you could go from, you would need to go from here to here. So that is also very needed. To do all this, we have to learn this idea called Fourier transform. So what is Fourier transform? Fourier transform is the following. If, this is the definition of Fourier transform, if I have a function f of x, I can convert that into g of k by multiplying that function by e power 2 pi I kx dx. So I can define k appropriately. So very often you would also be represented, so here you would sometimes see g of k is f of x. You want to convert f of x to g of k, you have to multiply with e power minus I kx divided dx, integrate over dx minus infinity to infinity. If I integrate this, I will get g of k. Now, k can be appropriately defined, like k can be defined 2 pi by L, n 2 pi by L and all that. So k, if I define k as n 2 pi by L, and I can write this as a sum if I want, right. So then if I do that, this has a connection with Fourier series. So you might remember, you have an f of x, you multiply with e power I k x or sin x or a cos x, right, because I can write this as sin x and cos x. So let us write this. So this thing is called a Fourier transform. This conversion of f of x to g of x, this integral, this transformation, this mathematical transformation is called a Fourier transform, and this has a lot of use. We will discuss how this is useful. But immediately one thing you can see is that this is a connection with Fourier series, of course. So if I just write g of k is equal to f of x e power minus I k x integral dx minus infinity to infinity, I can write it as f of x cos kx minus I sin kx, and of course this integral can be written as a sum. So I can represent it as sum of the whole thing. So now depending on the limit of the sum, so you can see that this is like the integral one would do, or I could do an so this is like an integral. If this was an integral, instead of this is an integral, this integral is something that you would do to calculate the coefficients. In the Fourier series, to calculate the coefficients, we did this kind of integral. So these are the integrals we did to calculate the coefficient of the Fourier transform, Fourier series, and therefore there is a connection. In the Fourier series, we needed a periodic function. We needed a repeating periodic function. Here, this is the analogy here would be, it's like period or the length going to infinity limit. In that limit, that is equivalent of a Fourier transform. I wouldn't go into the details which you could read and understand the details, but for this purpose of this course, it is enough to understand that if I have a function f of x, it can be converted by doing an integration to a frequency space, and you can convert back. So if you can also do an inverse Fourier transform. So if I do have an f of x, I can convert to g of k by doing a mathematical operation, which is an integration. If I have a g of k, I can get an f of x by doing an integration. Now, doing this integral in reality could be difficult because this f of x could be some complicated function, or g of k could be a complicated function. But nonetheless, at least we can calculate the area under this function, f of x e power I 2 pi kx. So we can calculate area, and that is nothing but the integral. So numerically one can do the integral always. Analytically doing these integrals might be very difficult. But if I can plot this f of x e power I 2 pi kx and calculate the area under this, that is going to be this integral, and I would get for different values of k, if I do this, I would get g of k. So I can numerically compute this integral and compute g of k. Now why is it useful? Let us think of, so now we know that this has a connection with Fourier series, and we know how this is done in the case of Fourier series at least. Now let us think of some simple example. So simple example is, if I have a wave-like function. So if I have just sine 2x or cos 2x, right? So if I have some function, let us say it is some wave-like function. So if I have a function like this, so this could be some combination of sine and cos. So in general, this can be written as cos kx plus I sin kx. But it doesn't matter, you could take cos kx alone. If I do the Fourier transform of this, so if I do a Fourier transform of this, so this is my f of x versus x. This is a function of x, and you will get a curve like this as a function of x. Now if I just want to plot g of k versus k, how would it look like? For this particular function, if I do the integral that we like, the answer will turn out to be just one peak. Just one peak at some particular value of k. So whatever be the value of the k here, at that k, if k is 3, this will be 3. If k is 4, so this k would be 3 if this is cos 3x plus I sin 3x. If this is my function, then I will have just a k. Or if it just cos 3x, I would have some function k equal to 3. I will have just peak at one particular point. So this whole thing is now converted to just one peak, one function, which is called a Dirac delta function. So mathematical definition is the following: e power I 2 pi kx is delta of k if e power 2 pi I k minus bx, this is delta of k minus b. So in this example, in the earlier example, if we have b equal to 3, for example, if I have some particular sin kx or some particular value, then I would have, if I have e power I k minus 3 x dx, if I have integral, this is just like e power I kx, e power I k 3x. These are two functions. So both are, and I do integral of this dx, I would get delta of k minus 3, which is like a peak at k equal to 3. So that's what this says. So if I have a function e power 2I pi kx, this is delta of k, and delta of k is plotted. Delta of k is called a Dirac delta function, which has value only at that point. Everywhere else it is 0. So such peak functions, single peak functions, are called Dirac delta functions, and delta of k minus 3 means a peak at k equal to 3 alone. Delta of x minus a means a peak at a alone. So this function is what is plotted here. So if I plot this function, it would look like this. So functions with just one peak are called delta functions. So delta of x minus a would mean at x equal to a there is a peak. So if you have a nice oscillating function, it is likely to have a Fourier transform which is just one peak. Now if you have more complicated function, if you think of a music, what is a music? Music is essentially some kind of a combination of sines and cosine with some complicated manner. So many of you would have seen this patterns of music. What would you get? You would be getting some complicated pattern like this. The sound amplitude and its frequency would change and all that. A lot of some music like this. Now this is your f of x. I can do as a function of x, I can do a mathematical operation and convert it to a g of k. And the mathematical operation is what we described. It is an integral, that is, multiply with this e power I kx and find the area under this. That's all you have to do. Multiply this with sine and cos and find the area under this. So first multiply with cos, find the area, then you multiply with sine, find the area under the curve. That is like integration, and from that you can get this g of k. Now imagine that if the g of k looks like this, something like this, so if this g of k looks like this, if I store this much information, that is this peak positions and the height of the peak, only two less information here. So I have to just store the peak positions and the height of the peak. If I store this g of k information, I can construct this back. And if I store only the dominant if I store the dominant peaks, so I might have very small peaks which is negligible, but if I store only the dominant peak, I can reconstruct approximately this music. So this is what is typically done, for example, in the MP3 music, like roughly this is what is done. You might have heard this thing called MP3. So MP3 is a format which many of you might have heard, MP3 format, which is some kind of compressing format. So if I have this complicated music, I can do some mathematical operation which is the Fourier transform. I can convert this to this and I would get just g of k, which is going to be much simpler than that. If I only store the dominant peaks in this function, and then I can throw away all the other peaks, that would help us compressing this and storing much lesser information, and whenever we want we can reconstruct this back. How do we do this? This is what we just discussed. How do we do this is what is discussed. If I have this function f of x, I can multiply with this cos kx and then integrate. I can multiply that with sin kx and integrate minus infinity to infinity, and combining these two, cos kx plus I sin kx, would give me g of k. So basically, this is all I have to do. If I do this and sum, I would essentially I can get g of k. So if I do this integral and this integral, I can essentially calculate g of k. So for every k, I do this integral. First I take k equal to 0, I do this integral, then I take k equal to next value. So k would vary, is a continuous variable again. I could take various values of k and I do this and I plot g of k versus k. And I can store this information which is equivalent of storing f of x. So that is what is happening in many of the, this is also true for JPEG figure. So even if you have a figure, if you have a photo, what you have essentially is a two-dimensional information. You have some picture which is, as we said, it's some two-dimensional pixel information which is x and y, and what you have is f of x comma y. And this you can convert this to g of kx, k1 comma k2. I can convert this into a g space by doing a similar transformation both for x and y separately. I will get k1 and k2, and then this you can convert back. So this is what is typically JPEG and all that. The compressing formats of pictures, they convert this lot of pixels into some peaks in the g function, as a g function of k1 and g function of k2. I make some peaks, and then that would give us this, that will help us to store this information. There are many applications. Another application is in scattering experiments. So, in scattering and diffraction experiment, the output one gets is g of k. Example, X-ray scattering, which would find us the crystal structure. So this is what is very often used in many kind of experiments. As we said, also briefly mentioned in the last class, that I have the shape of a protein which is my function. I can send light or I can send some kind of electromagnetic waves, and that would scatter, and you would get some measurement which essentially will be like the g of k. And by doing some mathematical operations to that, one can get f of x, the function which is the shape of the protein itself. So this is the application that we have. So let me just remind you the basic principle. So you have some shape of a protein or shape of any structure that you like, some structure, and you do some experiment, and what you would get some other function which is g of k. So which would be like, which I would draw as some kind of peaks. It could be more continuous function like this, it could be some continuous function like this. So I would get g of k as a function of k. Now how do we get, and one can get this back by doing this operation? What do? You have to either to go from here to here mathematically, as I said, I have to take this f of x, multiply with cos kx and integrate, and then multiply with sin kx and integrate, and these two integral together will give us this. And if I do this and integrate back, I would get this back. I would take g of k, and integrate with cos kx and sin kx with appropriate signs. So if I have function g of k, how will I calculate f of x? I have this experimental data g of k, and now I want to calculate the shape of the protein in the real space. I would first multiply with cos kx, and then integrate over dk minus infinity to infinity. So this, if I do this, I would get, for a given value of x, integrate over all k, I would get f of x. Similarly, so this is one thing I will do. Then I would do g of k sin kx. I have to do both. If I do both, and from this together, this and this combined, I can get this f of x. So I do these two integrals, multiply with sine and cos, and I do these integrals, I can get f of x. So that is the procedure that we would follow. So one can use Fourier transform and other similar transform to solve differential equations. So this is also very useful to solve some differential equations, which we wouldn't discuss now, but in an advanced topic you would learn that how to use this idea to solve some differential equations is very useful. As we said just now, I can write e power I kx as cos 2 pi kx minus I 2 pi kx, and then this can be written as a cosine or sine transform. It's called trigonometric transform sometime. And if it is odd function and even function, some of this sine integral and cos integral will be 0, and appropriately we could just write only one of them. So these are some simplifications which you can think about it, which are mathematically useful, but physically what is important is that if I have some function in real space, which is the space that we see, which is the f of x, I can convert that into g of k and back. This is very useful, and that's where we use the Fourier transform. With this, I'll stop this lecture and continue in the next lecture.